Can you hear me? Good. Okay. It's a new mute button I didn't know about. Okay, I don't know what that means. Let me give people a couple minutes, or 90 seconds. I got the haircut I promised. Yeah, exactly. See, I'm back to normal. That's good. Very fresh. That's my first haircut in a long time. I'm pretty excited about it. I mean, one of the advantages of being a professor is you can have crazy professor hair and people will not think you're insane. But, there's a limit to how much crazy professor hair I'm willing to have. Kind of comes and goes. So I can dig up. No, I can't. All right, it's gonna take too long. I was gonna find my hair when I was like 18. It's pretty comical. Okay, some other time. Maybe when we do our life Q&A next Friday. All right, number's still growing, so I'm gonna wait one more second until the participants number stabilizes. Oh, it went down by 1. Okay, that's my cue to go. Hi, everybody. Good to see you in real life-ish, sort of. Thank you to my 3 faces I can see. I appreciate it. Yeah, I hope GitLit's tweeting. Oh, wow, we got 5 now. So I hope everybody's, doing okay with GitLit. If you are struggling, make sure to fill out that form I sent last night so I could just get a handle on it, and I will try and deploy things to help you out, especially people who have been really looking at the resources and really, really, really giving it a genuine, hard try and have just hit a brick wall. See what we can do. Keep in mind the office hours will be way better starting tomorrow, but obviously if you're really hitting a brick wall, you probably want someone to talk to, maybe on a scheduled time rather than uncertainty of an office hours queue. So I don't know, I got some ideas. We will see. It is a grand experiment, GitLit, this semester. And I will be very curious to hear your feedback on things later. I think it's a very good project. I think you'll learn a ton, but it is arduous. Okay, let me share my screen and let's start talking about software engineering. So this lecture is a bit of a pivot from the other lectures. And the reason I'm doing a live version of this is just the class has moved enough from, like, in terms of the content, especially with GitLit, than where it was when I first did this lecture in spring 19, that I just wanted to do a new one. And rather than pre-recorded, I also just thought it'd be fun to like actually do a lecture and get to see people for a little bit. And so the idea behind this lecture is that in the olden days, when 61A and B were not quite so packed full of content, there tended to be lectures that were more focused on real world stuff. So 61A quite famously, this is not in scope for the final, that's right. This lecture I think is useful for the 2 reasons. 1, it may help you with GitLit and Project 3. And 2, I just think for your future life, the philosophy in this lecture, I'm proud of it. I re-listened to it on the way to my haircut today. I was like, that was pretty good. I'll see if I can match me from spring 19. But the basic idea here, not on scope on the final, just to be clear. So 61A used to be Monday, Wednesday technical. And then Friday was some bigger picture topic where you'd get like an industry speaker or someone to come talk about privacy or whatever. And this is circa like 2000 or so. But then over time, both 61A and B and C and 70 have just sort of like accumulated more and more content. I've actually cut 61B to some degree from where I had it a few years ago. I'll probably trim yet more. And this lecture is one of those. We're just trying to bring some bigger picture philosophical stuff because I think it could be more valuable to focus on these things than to learn one more like hash table variant or whatever, right? So this is a continued experiment. It's worked so far in the past. I don't know if I'd still call it an experiment because I'm kind of into it. Where for the next 3 weeks, I'm gonna have 1 lecture a week that are dedicated to these sorts of topics. And guess what? They're less stressful to listen to these lectures. They're out of scope and they're philosophical. Gives you a little more breathing room. And once you're done with GitLit, like the class is actually more chill. Project 3 is big, but it's not as big as GitLit, and it's more fun, I'd say. It's like more free and more creative. Okay? So now I'll note, as I said before, this is a very different flavor lecture. It's not really technical, it's more philosophical, but I think you'll still like it. So the motivation here was that in general, the way 61A and B has how your intro programming classes have worked so far, they've kind of misled you about what programming entails. Often you're just opening up a blank file and then just getting to build, whatever you're supposed to build. And the thing you're supposed to build has a very limited functionality. So in 61A, that often meant here's a function, fill it in, right? And in 61B, except for project 2 and 3, it's been here's a class like let's say the 2048 model class or the linked list deck or the array deck. It's like this is a class. This is the spec. These are the methods. Just go do them. Project 2, GitLit. I mean, I think the thing that's really valuable and interesting is I think it does mimic the process of real software building pretty well, in the sense that you're just in this wide open space where the way you're interacting with your program is weird. It's like you're interacting with the command line, and it's just the storage, like the state of the program is persistent between runs. It's all a little strange. And being able to do that, I think, is really important. And in the long run, whether or not it should be in the middle of 61B or not, still something I'm trying to understand, just be aware. But these projects, other than project 2 and 3, it's always been a little, here's just something to fill in, right? And project 2 has been your first foray into this real world. Now, one of the things about working at a small scale like you have in all other projects except for GitLit is that I think it gives you habits that will cause you great pain later. And some of them you may have already felt in the course of doing GitLit. So what I'm going to do in these 2 lectures, and then the third lecture is more about impact, social impact. I'm going to try and give you a sense of how to deal with the large scale. That is, when you're building GitLit or you're building the Build Your Own World project for this class, that'll be project 3. When you're building real software, I'm going to try and give you tips for that. Now, one thing that's hard is that in a lecture, it's hard to find a task which is small enough to actually fit in the lecture, but big enough to show the big picture issues. So I got a couple ideas, but it's going to be more philosophical than like us actually building software together. Project 2 and 3 actually let you do this. You've already been struggling through this. So maybe see how the philosophy, which we'll get to now, how that applies to your experience so far. Okay. So again, even though this is not in scope for the final, what I hope is that this will help you reflect on your project 2 experience so far, and will help you do better with project 3 in terms of being strategic in your thinking. Now, I should note that these lectures are based heavily on this book called A Philosophy of Software Design by Professor John Osterhout. His daughter, Kay, was actually one of my TAs when she was a PhD student here at Berkeley a few years ago. And this book is actually in part inspired by some of the work that Kay and I did on 61B together. Maybe I'll tell that story later. But if you like this lecture and you want to know, like, okay, what is the bigger story here that John had to say, go check out the book. And the reason I like this book is that, over the course of my life, I've learned a lot of these lessons, but I hadn't reflected carefully on them in the same way that John Osterhout had. And so it really resonated with me. And I said, yes, that's what I believe. You've said it beautifully. So let me rephrase it for my students. So I have said before that complexity is the enemy in computer science. And so I'd like to define complexity in some way that is useful to you, right? Now, the reason that complexity is so important is that in the world of computer science, complexity is the limit. Like, it's not like other disciplines that you may study. Some of you may be, chemical engineers or bioengineers or like, of those of you who are engineers, there's these other domains that you may be in. Software is interesting in that it's not constrained by the laws of physics. I mean, it kind of is, because computers only run at a few gigahertz and have a few hundred or million or billion or trillion bytes of memory. But that's not really a limit. I mean, it's like a soft limit, but it's not at all like the limits that other disciplines face. When it comes to computer science, the limit is you, like your mind. Programming is an act of, I think, of almost pure creativity. What I mean by this is that the limits of me being able to build GitLit or the Build Your Own World project or 2048 or Facebook or whatever tool out there is being able to understand what we're building, right? It's not like other disciplines like chemical engineers where you need to worry about temperature, where as I'm building a system, I need to think, oh, well, it's going to get hot and I need to radiate all this heat away. And so that's going to constrain my, the diameter of the pipes I can use or whatever. Or material scientists, they have to worry about brittleness, right? Whatever the right appropriate abstraction is behind the material properties of the things they're thinking about. Civil engineers need to worry about the strength of concrete. When I build a bridge, I can't just say, well, the bridge strength is 1 million, right, or something. It's not some constant I just set. I have to know about the physical world around me. Now, limits are great. I mean, they're part of what makes life good, right? Like that's like the limits that are placed upon us Like if you're free to do whatever you want, life's less interesting. If you ever cheated at video games, you know this. And so the limitation, even in software, there are limits, but the limits are creativity. And I think that's a pretty unique thing. There are other disciplines that are purely creative, like say mathematics, but computer science, I'd say, has the additional feature. Like when I think about what's the difference between computer science and math, to me, primarily just from my perspective, I'm kind of going off on a tangent for a moment, but I think of computer science as it's a little special in that the math you're building, that there's a machine that brings it to life, right? Like I think of an idea of how one could implement 2048, and then I write the code, and then there's a game I can actually play. Like it is just math, but it's math that's brought to life in some way. And so I think for me, it's always been a really cool sweet spot in terms of disciplines. Okay. So as I've said, the limitation is understanding what we're trying to build. And the issue is that as you build a real piece of software like 2048 or GitLit, they're going to gain more and more features and complexity, right? Or if you're building PowerPoint or Google Slides or the Chrome browser, they're going to get bigger over time. And so what happens is that over time, it becomes more and more difficult for a programmer to understand their own code, to understand other people's code, and it's just hard to understand all the relevant pieces as you make future modifications, right? Because it's a castle of mind, you know, it's this just beautiful palace of mental output that people have put together, and eventually it just gets too big to hold in your brain. Now there are ways to fight this, like IntelliJ, right? IntelliJ is built to help handle complexity in the sense that, you know, there's ways to navigate around and say, hey, where was this function declare? Like where's the file that has this? You know, JUnit tests help you by building confidence in the basic pieces. The IntelliJ debugger helps you find bugs, and the visualizer, it helps you see where problems are. But, you know, all of these are just like, those are the tool end of dealing with complexity. And so I'll talk about the ways that you can approach solving problems in order to avoid complexity altogether. The number one thing, if I have any takeaway for this entire lecture, it's just that your goal should be to keep your software simple. And we'll see some ugly software, and we'll think about how to make a beautiful software in a little bit. But that is really, to me, what matters, okay? Now, how do we manage complexity? And I will tell you what complexity is in a moment, but what are the ways that we manage complexity? How do we keep our programs from getting super ugly? Well, John Oosterhout, I guess we'll call him Professor Oosterhout, he has two key tools, which, reflecting on my own practice, I absolutely agree with. I think it's cool that he's bunched it this way. One is making code simpler and more obvious. That means eliminating special cases. So we've actually seen this. Like this is the practice we saw way, way back when we were doing our list lectures. We were building S lists, right? You may not quite remember this detail, but there was an issue when we had a singly linked list data structure in week 2 or 3. We had an issue where when the list was empty and we called add back, then the code would crash. We could add a special case, but instead we added sentinel nodes. So even though, you know, sentinel nodes take a while to understand, when you wrote your linked list deck, if you use sentinel nodes, which most people did, it makes your code simpler and more obvious. Everything's the same, everything's kind of flat, and it avoids complexity. So sentinel nodes are an example of managing complexity that's a little subtle. Yeah, exactly. If someone puts, it's easier to have a sentinel node than special cases everywhere. Okay? The second approach that he recommends is encapsulation into modules. Now, this is a very difficult notion, but the idea is that in a modular design, creators of one module can use another module without knowing how they work. Okay, so for example, the design of 2048 as we presented it was not particularly modular, and that when you wrote your tilt method, you may not quite remember this detail, but there was a bunch of kind of funny things you had to do where you had to set the changed variable equal to true, and you had to call set changed, and you had to call our specific move methods in a certain way. Ideally, a design would be so clean that you wouldn't have to really know about those kind of details. You'd be returning maybe true or false. I don't know exactly what you would do differently, but the idea is like, I just want to be able to use your piece without knowing about the internals, okay? Another example, though, I mean, we've actually seen this idea all over the place in the sense that with a deck, you don't need to know if it's a linked list deck or an array deck under the hood. But this principle, you'll really get to feel this when you do project 3, right? So in project 3, it's a pair project. But what you'll find is it's hard to come up with modules where I can just like ship them off to somebody else and they can just use them. But these are 2 things you should strive for. Okay? Yeah, exactly. Abstraction barriers and the cave analogy. All right. So complexity. I've been telling you how to avoid it, but I haven't told you what it is. I will borrow John's definition. And I love this definition. I think it's a perfect definition for software complexity. It's anything related to the structure of a software system that makes it hard to understand and modify the system. What I like about this definition is it is human-centric. It's about your ability to actually do something with the code, right? It's like, I can't understand this or modify it. That means it's complex. Okay? So it takes many different forms. We see complexity in many different ways. One is understanding how the code works. That's an example of complexity. If understanding how it works is difficult, then we say the code is complex. Another is the amount of time it takes to make small improvements. Like I have 2048 on a size 4x4 board. Now I want 5x5. If my code is complex, then it will be a pain in the ass to do that. If my code is simple, it's probably just a constant I need to modify. Another is, what do I need to modify to make an improvement? Like figuring it out. So if code is complex, it may be difficult to even look through the code and understand how would I make this a 5x5 version of 2048. But in a less complex system, again, maybe it's just a constant at the top of the file. Another is that it can be difficult to fix one bug without introducing another. One of my TAs sent me a Reddit thread you may have seen of fix my bug in GitLit, 3 bugs popped up or whatever, right? Like it's a hint that there's something complex going on under the hood. And so as he puts it, if a software system is hard to understand and modify, then we say it's complicated. If it is easy to understand and modify, then we say it is simple. Okay? Now this may also seem a little like trite or simple or like not very deep, but I do think there's a lot of depth to this. I think this is really, if you think about this at the center of when you're writing big code, I find it really helps. One thing I will just throw out there as a let's see, yeah. I just want to look at the chat real quick. Okay. One thing I'll just mention in terms of, oh, sorry, I haven't gotten to the weird thing yet. Sorry. I lost my train of thought there for a second. Okay, so as John puts it, complexity, the peril is that it costs you something. So in the cost view of complexity, it's basically about human effort. So in a complex system, it takes a lot of effort to make small improvements. And in a simple system, bigger improvements require less effort. So let's talk about tilt in 2048, just as an example. I'm gonna show you some complex code. Now we already did this for the project 1 peer review, but let's go all the way back to tilt from project 0 and get a sense of a way too complicated tilt method. So this right here is a hybrid of some different student solution with some TA code, but it's basically one way that you can try and do the tilt method, okay? And so what I want to do with this real quick, make sure I have my right thing shared. So this works, right? This is a method that does actually work. It's pretty long, and as you can see, it's really unrolled. And if you wrote code in this class or ever in your life that looks like this, you should not feel bad, right? Like when you're learning how to program, this is an example of like, well, it's gonna work. I'm just gonna, you know, it's like sewing. You know, you have this impression that I'm gonna do one line at a time. Eventually, it'll work. Instead of learning how to do the sewing machine version, I know how to do the easy thing. I'm just gonna go and go and go until it works. And someone did that with this code, which I've modified a fair amount. But yeah, and so we think about it. We're working our way through the 4x4 grid, and basically there's some special cases, quite a lot of special cases. You know, if y minus 1 is less than 0, well, then we're gonna pull out of this operation. Otherwise, we're gonna check if it's null. If it is null, we're gonna do some stuff, and then we're gonna do this next one and so forth, right? So this is yeah. So this is intense code. It's quite difficult to understand. But I kind of want to get in your words, like what are some things about it that make it complex, just based on what I've been saying? So I'm happy to take some spoken comments or some chat comments? Yeah, I got a lot of lines. Okay, yeah. Too many if statements. All right. Yeah, repetitive. There we go. Yeah, so we got the code is repetitive, and I think that's a big problem. There's no English to describe what's happening. So even though you might have understood when you wrote it, it might be really hard to follow later. Yeah, we don't quite understand what each statement does. Hard coding values, right? We got all these 3s and these 2s and these 1s and these 0s. Yeah. And as Austin points out, the redundancy is a really big problem, because if we need to change something, like we find out there's a bug, you know, oh wait, I don't need to actually do score plus equals 2. Maybe it's supposed to be 3. Now I need to go through and change this in all these other places. And you know, maybe I miss one because I'm scrolling through my code. Like, okay, I don't see any more. Maybe that was it. But actually, you know, it turns out when I was scrolling through this, I probably did miss at least one. That redundancy will really bite you. Okay. And so these are all reasons why, you know, this is a more extreme case, a little bit artificial, but you know, it's not unreasonable to think that a 61B student could produce code that's pretty similar to this. I see it all the time. And it's just part of the learning process is realizing that this is something you should just not accept for yourself, right? Yeah. Let's see. You are right. You can do this. You could say find and replace. Let's see if it gets them all, though. Okay, I'm just kind of curious. Okay. All right, yeah, that one worked. So you can do that too. But there may be other more subtle changes where it would be a pain. Okay. The reason I bring this up is even now, like in your Gitlet code, it wouldn't surprise me if you have similar redundancies. I mean, the discussion of like whether or not one should have a blob class or not, like actually, let me tell you an interesting debate we've had on the TAs, which is in Gitlet, where should the staging area be represented? And I think there's two basic schools of thought. One is in some class, one idea. Where should the information about the staging area have that? Another idea is in the file system only, right? So there's no actual explicit like instance variables that store anything. It's just a bunch of files. And I don't think that we've come to a consensus among the staff which of these two approaches is better. But you know, it's like sometimes it can be really hard to tell where you should have redundancy, because you could argue that this is redundant, but it also makes things simpler. So these debates can be very challenging. Yeah. Yeah. Okay. So that's something that's definitely too complicated. Yes, whatever gets past grade scopes. That's what I'm trying. This lecture is about avoiding that temptation. Okay, let's talk about another example of complex code. When I mention complex, I mean, obviously the piece of code I just showed you, which was, you know, almost 300 lines, where maybe 50 or 40 lines of more modular encapsulated code would suffice. You can get complexity in all kinds of situations. So what I have here is a picture. Anybody here take CS10? I taught CS10 once, and I'm doing it again next fall, and I'm super excited. Yeah, it's such a good class. I love it. It's so good. I love this programming language. I like everything about CS10. In fact, actually, what's kind of fun is I think tentatively in the fall, I hope to teach CS10. And in the spring, I want to teach a functional programming course inspired by how much I love CS10. That will be more advanced. That will come after 61B. But anyway, this is a piece of code for the game Battleship. If you've ever played the board game, one of CS10's features is that you get to build whatever you want. And this is actually someone who was in CS10 and later was my TA for CS186, a head TA, or a 20-hour TA at least. And so they went from writing code that was pretty sloppy. Let me read this to you, even if you've never seen Snap. If ship hit 1 equals true, and ship hit down equals true, and ship hit right equals true, and ship hit up equals true, and ship hit left equals true, and none less than 91, a little mysteriously, and not this, and not, I mean, like, it's a mess. And the point is that this code is hard to understand, modify, and it seems like clearly whatever this is trying to do, it must be quite redundant. Okay. Now, again, if you're somebody who's written code like, oh, no, here we go. You want to see this code? Thank you. I'll let you stare at it for a second. I've only been Zoom teaching for 1 year now. Anyway, so this code, which you can now finally see, thank you, chat. It is a bit of a mess, but this person grew and they got better at it, and hopefully they avoid this. Yeah. Yeah, this language is called Snap. It's a variant of Scratch. What I like about Snap is it has some really good visual metaphors for how one can do recursion and higher order functions. It's just so good. It's just amazing. Passing around functions, magic. Snap nightmares, no. There are no snap nightmares. It's just good. All right. Let's mention just briefly a sidetrack about complexity. So I've been telling you that complexity is bad, but complexity is unavoidable, right? There's just some things that are hard to do. Like, for example, if I'm trying to write a piece of software that is able to, I don't know, drive a robot car around and track a piece of tape on the ground or whatever, it's an inherently complex task. Or if I want to write a piece of software that can play StarCraft 2 against humans, it's complex. It has to be complex. And so that's just something we have to deal with. The other thing is that sometimes even like relatively simple things, like I want to simulate the trajectory of an ordinary differential equation. Like I have some initial conditions and I have an equation and I want to use like a Runge-Kutta solver to watch the system evolve towards its later state. Like it's a complicated piece of math, you know, all these, like if you've probably never done Runge-Kutta simulation, but you've probably done like a trapezoidal approximation of an integral, like that kind of thing. Like there's a lot of depth to the way you think about it. And so the code's going to be just a little hard to understand because the math, even though it's like compact in size, is hard to understand. And so those pieces of code will often be complicated. So what John notes is that we should also think about how often a piece of a system is modified. Because remember, complexity is a human-centric definition. So if there's a little core of your code that is highly complex, but almost nobody ever looks at it or modifies it, then the overall impact is minimal. So if you need to write some ultra tight, ugly, kind of hard to understand, really mathy code, then that's okay. And maybe you only have a few people on the earth who can understand how to, like, you know, maintain the backpropagation algorithm at the center of, I don't know, TensorFlow or whatever. That's okay. That's something you're willing to accept. He even puts a math formula to this, just for fun. I'm throwing it out there, which is you can think about the complexity of a piece of software or a part of a piece of software, P, as the sum of C sub P times T sub P, where C is the complexity in arbitrary complexity units, and T is the time spent working on that piece of code. And when we say working, we mean actively engaging with it in some way. And so if you're not really, as an organization or a person, looking at code very often, maybe it's okay to leave it as a bit of a mess if it's somehow much more efficient. I don't remember my MMR or League. I hadn't played SC2 so long ago. I was in, I mean, it's different, right? Because the game is, I was playing in like 2011 or 12, and it was a lot easier. I was in a Platinum League, I remember at some point, but I don't know what that means now or then. So, yeah. Anyway. Yes, exactly. That's when it was. I mean, I was reasonably good. My hands are too old. I used up all my clicks. I like the idea of playing StarCraft is like vaguely nauseating to me now. So I don't want to hurt my hands. I mean, I can, but yeah. I have kids now. They're like, it's like StarCraft, but harder. Anyway. I don't know where the metaphor, how that works at all. Actually, the main activity I'd recommend to everybody is surfing. All right. Complexity. Okay, how do you know your code's complex? I mean, we had some obvious examples, right? Like that piece of code we looked at in the notepad or the Sublime text. But I want to talk about just ways that you can observe complexity in your own code, because when you're writing code, often it doesn't look so bad to you. So the 3 symptoms of complexity, and again, his book's really good. So that's why I'm using his framework, because it is cleaner than the way I would have put this. The first is change amplification. You'll see this. You may have seen this already in Gitlet. You will see this in project 3 for sure. And it's if you have a simple change, right? Like I want to use the W key to move north instead of the in key to move north in some software you're building. If a simple change like that requires a modification in many places, for example, maybe your game accepts input from the keyboard or from a file or from a web player or from an AI player. If it means then you need to go and modify like 4 different files to process the input to your game differently, let's say, depending on who the player is, human versus AI versus like a replay file or something, then that's an example that's a symptom of code that is complex, right? 2048, as we saw, our overly complex version, was also an example of that. If I wanted to make that a 5x5 game instead of a 4x4 game, it would be a nightmare. It would actually probably not, like it would take you, a day to figure out how to like take that piece of code and bend it appropriately. Cognitive load, closely related but not quite the same thing, which is how much do you need to know in order to make a change, okay? Now, you might see this whenever you're working with your partner on project 3. Maybe, so just as a very brief preview, if you don't know what the project is, it is a project in which you build a world generator. So it's a random generator for a 2-dimensional world. Like if you've ever played a roguelike game, or I don't know, you can think of it as 2-dimensional Minecraft maybe. It's kind of like that. And what you build isn't necessarily a game. It's just a world generator. Maybe it's just purely artistic, but there's a lot of pieces. And so if you need to know a ton about the program, about the pieces of how things are built in order to make any kind of change, that's an example of high cognitive load. Okay. Now I'll note that it's not the same thing as the number of lines of code. I would say that you may have seen this annoying thing that I do when I program, which is that I'll sometimes define a variable on one line, and then on the very next line, I just use it immediately, or maybe just return it, right? Like, int best result equals blah, 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 return best result. That's an example of code I've written slightly inefficiently to reduce the cognitive load just a little bit. It's kind of a silly example, but I do it a lot. Incidentally, I should note, you may have noticed I don't ever use plus plus or minus minus. And actually, I'm going to go open up a notepad window to kind of showcase why I don't like that. So for those of you who have never seen this, but you will see it if you take 60 on C, it is possible to do things like, let's say we have an int array x, and we do blah, blah, blah. We don't know what's in there. And then we want to do return. You can do like return xi plus plus, for example. Like that's a thing that's allowed in Java. And I'm not a big fan of the style. Who would you like to FaceTime with? Hello. Uh-oh. You're unmuted. Okay. Anyway, yeah. So this right here, this is code that returns xi, then then also increases, then afterwards increases I by 1. I don't like this kind of coding. Maybe you like it, but I'm just not a fan. People do weird stuff like wall xi plus plus. I feel like the Princeton code's full of all kinds of stuff like this. And this is a case of personal aesthetics. I'm just not a big fan of the style of programming because it's just a little too much to look at. I feel like the cognitive load is too high, especially when you end up having people do things like, minus j or something. Like this is an example of pretty ugly code, but I wouldn't be surprised to see things like it. It's just hard to reason about. Anyway, kind of a digression, but you may note like that my coding style tends to be like, I equals I plus 1, or let's say x return val equals xi, I equals I plus 1, return val. I don't know why you would do this exactly, but yeah, this would be the equivalent. Okay, anyway, digression, but personal style. Look at this chat. Okay. Yeah. Someone just asked, is it better to be more verbose and use more memory to hold more technically unnecessary variables to reduce technical load? I would argue that more lines of code and variables for lower cognitive load is better for 2 reasons. One, that the cost and performance is likely to be very small. Constant, like some constant amount. Okay, like computing is cheap these days. And the second and more important one is that modern compilers might just optimize out the inefficiency completely. So I suspect, but I'm not certain, that if we look at the compiled code for this and the compiled code for this, I actually think it might be the exact same thing. Like when it gets to the machine, like once it gets compiled into bytecode, which we haven't talked about, I think it might be the same bytecode. And then maybe even the next level down, which you'll learn about in 61C, I think it's just going to optimize to the same thing. There are really performant examples where you really don't want to do this, like the example I gave before of an ODE solver, where you need hyper speedy code and then it's written ugly because it needs to be fast. You know, I mean, actually, here's an example. Sorry to go one more on this. So merge sort can be written in many ways. There's the straightforward way, which you might see. The Princeton actually has a great set of examples of this, where they have, I think it's merge.java. Then you have like the more efficient way. I think they call it like merge x.java and blah, 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 .java. Like I would say the following. If you're writing library code, like if you are writing arrays.sort, you should squeeze every little bit of performance out of it and not make it simple to look at, because as noted, like this is a piece of code that's probably not going to get touched for years, and it's so important. So even though no one's really looking, even though it's really important and maybe kind of complex and ugly and has high cognitive load, it doesn't get modified very often, and its performance is super important. So it's kind of a case-by-case basis. Yeah. It is true, by the way, that ++ is pretty satisfying to do. So, you know, I don't hate it, but I have done various practices in this class in order to discourage bad behavior. Another one I guess I'll note is that it is technically possible in Java to do something like this, like print 5. Like you don't have to actually do the braces. I always do it that way, even for one-liners, but they don't have to be there. But I haven't written code like that for so long that I actually was a little worried I was wrong, but I'm pretty sure I'm right. Anyway, all right. You know, your coding style will evolve with the organization you work at. That's how it's going to go. And you'll end up they'll bend your will as badly or worse than we did with our damn style check. Anyway, all right, oops. All right. So those are our first two signs of complexity. One, change amplification. Making small changes requires you to change a bunch of code. Cognitive load, the code's hard to understand enough to make a change. The last one is unknown unknowns, and this is the worst type of complexity. This occurs when it's not even clear what you need to know in order to make modifications, right? Now, certainly this is very common in large code bases, and you've already felt this a lot in Gitlet, right? Like when you get to the point where you're writing your own code and you're thinking, how do I do, you know, merge or checkout or something? Sometimes, even though you wrote it, it can be hard to tell what you even need to be modifying in order to make everything work. And so this is a pretty difficult symptom to diagnose, and it's going to be always there. But the more you can reduce that, you're good. And thank you for noting again that I have the wrong slides. I have a dream, by the way, of getting a wider desk. And on that wider desk, I want to have 2 monitors. And then you know what you can do with 2 monitors? You can see everything. Anyway, all right. So someday soon. I've started desk shopping. Okay, we're almost done with philosophy. Then we're gonna do a little exercise. I've never had 2 monitors, and I'm super excited about doing it for the first time. I'm gonna, you know, yeah. Okay. So wrapping up our philosophy before we do an exercise here. So in a good design, a system is ideally what the term used is obvious. What's an obvious system? Well, in an obvious system, to make a change, you can quickly understand how the existing code works, and you can come up with a proposed change without doing too much thinking, right? So if you look at our reference solution for 2048, which I can't share in the middle of this lecture, but when you look at it, it's very clean, and you get a very clear sense of like, okay, well, if I wanted to change the rules up a little, I know exactly how to do it. Things are named nicely. You know, there's variables, and the approach is so clean that it can't help but be, you know, obvious. I think that's the thing to strive for. And another really great thing is that when a code base is obvious, you should have a high confidence that the change you have made should actually work. Even though you don't necessarily read a lot of code, it's just like, okay, I can see that this function, like it does this very specific task, like finds the smallest item in the list, and there's a swap method that swaps 2 items or whatever. I can just tell that if I make this change, it's gonna work. If you have code that's written like this, it's good. Those are things you should strive for. Okay. All right. So where does complexity come from? So I should note that it comes insidiously and slowly. So every software system starts out beautiful, pure, and clean. For the most part, it's a blank file. Like even Facebook or Microsoft PowerPoint was at some point. Both of those software systems were probably 5 lines of code at some point. So they were pretty simple at the time. But as you build upon a piece of software, they slowly get uglier and uglier and grow spikes and just slime. And it's basically inevitable. Like you can't really fight it. You can try, but it's always going to get a little ugly. Now, every time you introduce one of these complexities, it's not really a big deal. Like I'm going to throw in an if statement for this special case. Or, I don't quite know if this should be starting with I equals 0 or 1, but I'll just try 1. If it doesn't work, I'll do a -1 somewhere else. And so what happens is that you have hundreds or thousands of these small little dependencies or obscurities that build up over time. And eventually, there's so many of these little issues that every possible change is affected by several of them. And this has certainly happened to you in code you've written in this class. I would say in 2048, in ArrayDec, whenever you're doing resizing, right? Whenever you're doing Gitlet, when you're doing project 3, you start feeling this. And when you build big software systems, this ends up being a big deal. And so the fact that this all happens incrementally is part of what makes controlling complexity so hard, because it's not necessarily like your design in the beginning was bad. It's just that it grows warts over time. Okay? Now, John Osterhout recommends that if you're building real software, you should really have 0 tolerance. Like when you start to smell your code or see your code having these bad symptoms of complexity, you stop, you step back, you refactor, you run against your unit tests, and then you proceed with your new, more beautiful design. Now, in the course of a semester, in a course at Berkeley, often you don't have the luxury of doing that because you have 3 other classes. This isn't your only responsibility. Maybe you have a job. Maybe you like sleeping. So it's like, okay, well, it's working good enough. I'm going to get it done. But be aware that whenever you want to build real software, maybe you have 0 tolerance. And in your future CS classes or in Project 3, maybe like smaller tolerance than you would otherwise. Okay, last thought. Great. Actually, I'm glad to hear you've been refactoring a lot. Okay, so last philosophical thought. So much or all the programming that you've ever done, other than Gitlet, I would say, Osterhout would describe as tactical. Your main focus is to get something working, such as a new feature or bug fix. Even Gitlet, probably the case. Now, it might seem like a weird criticism because working code is obviously a good thing. But the problem is if all you're focused on is correctness, you're going to run into trouble. So the problems with being tactical versus strategic is that you're not spending time thinking about the overall design as you go. Now, some of this is natural because I find it quite difficult to come up with the design from the very beginning and really stick to it because you kind of learn as you're programming. But if you're just being purely tactical, you don't really think about the design. You never give yourself a chance to do so. And so as a result, you end up adding all these little complexities like, well, I have these 2 copies of a method that do something similar, or 4 copies. I have, for example, tilt up, tilt down, tilt west, tilt right, something like that. I mean, we gave you an abstraction to avoid that, but it's a pretty natural thing to do. And so each of those individual complexities seems reasonable because they just need the autograder points or whatever, but eventually you'll feel the weight if you're really building big software. Now, refactoring would fix the problem, but it also takes time, so you end up introducing even more complexity to deal with the original complexities. Okay? And so project 3, in addition to what you've seen in project 2, it'll give you a chance to really feel that. But I think that in project 3, because the problem is a little more open-ended, it just feels like you'll encounter it in a more organic way. Okay, so the end result of all this will be misery. Now, I think project 3, you probably won't ever be super miserable, right? I don't think of it as a miserable project, but when you build bigger software, it can be bad. Strategic problem about programming is to realize that, well, working code is not enough. And so instead, what I need to do is look out for these complexities as I go. When you build real software, which, I don't know that this is a good idea in 61B, but if you're building real tools, like if you go and do a research internship or something, the most important thing really is the long-term structure of the system. The tools that we build, like the Beacon system that you guys have, we've really put a lot of effort into the long-term structure so that the next generation of staff can really understand it and improve on it. And that when you're being strategic, you should just think that adding complexities to get these short-term time gains is unacceptable. Strategic programming, of course, requires a lot of time investment. And again, it's not really compatible with a finite semester. And so as novice programmers, it'll seem mysterious and hard to be strategic. I would say that based on what you've learned in project 2, like in project 3, like try to really plan ahead and realize though that just like your Gitlet is likely to be super ugly, like I can almost guarantee your Gitlet's just gonna look just awful unless you do it again next year or something. That'll also happen with project 3. All right. So a couple strategic programming tips. For every new class or task, rather than just implementing the first idea you have, try coming up with and maybe even partially implementing a few ideas. And then when you get the one that feels good, you're like, yeah, that seems nice, then fully implement that idea. I did that with my project 3, where I had like 2 or 3 different ideas about how to generate my world. But it was only when I got sort of halfway through exploring the third one, I was like, I think this one's going to work. And it did work pretty well. And then in real systems, not in 61B, try and think about how people might want to change your software in the future, right? Like, oh, well, maybe we need to support, users from multiple different, I don't know, universities or something. And make sure your design can handle such changes so that everything isn't just hard-coded to accept users only from one email domain, for example. Okay. As an example, in project 3, you're going to have to be able to interact with your 2-dimensional world. And so you'll need to support input from both the keyboard and input from a string. So think about that. So to wrap up this, before we do one brief exercise, I will say this. Strategic programming is really hard. And no matter how careful you try to be, there's going to be mistakes in your design. You just can't avoid that. So you should avoid the temptation to patch around the mistakes, but instead fix the design. Now in Gitlet, again, like that design is, I think, big enough that really stepping back and trying to heavily refactor the design in the middle is just too hard. But in project 3, I think you will have the flexibility to do so. Even though in the middle of a project you could do this, so instead of adding a bunch of special cases, like have the system gracefully handle the cases you didn't think about, I don't know, with exceptions or something. And we saw this earlier with Sentinel nodes for S lists. And I should note that in large software systems, it's like basically impossible to design them entirely in advance. I don't know how to do it, at least. So it's all kind of a learning process. I'm going to skip my thoughts on Facebook because I want to do my exercise. Basically, this slide is just back in the day, Facebook's infrastructure was very tactical, and it was miserable to work there. Now it's better. OK. So the last thing I want to do is just introduce a task, and let's chat a bit about how we can decompose. So in project 3, you're going to build a 2-dimensional world, and there's a lab you're going to do next week where you're going to build a not the project 3 world, but sort of a Settlers of Catan board. So if you ever played the board game Settlers of Catan, this is an exercise I put together as a warm-up to project 3 based on that game. Okay. So in this lab, what we're going to do is build a piece of software or part of a piece of software that will build randomized little boards like this. There's little hexagons here, right? So this is a hexagon that's size 3 at the bottom. This is a world where the hexagons are size 4, and there's different textures. So mountains versus plains versus flowers or whatever. Okay. And so one of the most important principles is decomposition into parts, often implemented as classes or helper methods. So my question for you, that I'd like to just take some suggestions before we go, if we're trying to think strategically and think about decomposition, what are some potentially useful ways to decompose this? What are some potentially helpful methods or classes? So just throw out some thoughts in chat. I never worked at Facebook, by the way. Make a hexagon, right? OK, yes. OK, so maybe a function that prints out a hexagon. Something that can output a tile, sure. When you say make a hexagon, what do you mean? I mean, it's obvious that some kind of making a hexagon. Would you, getting a random icon? Like, do you think like, OK, so what would a hexagon class? Yeah, I agree. So a hexagon class being an object would be great. So hexagon has color properties. It has, what else? Yeah, size, sure. Yeah. So we've talked a lot about how to like create an individual hexagon. How do you actually get this tessellation or this grid of hexagons? What's a function you might need there? because they have to be like perfectly lined up here. So, oh, it's interesting. Hexagon add neighbor. Okay, let's see. Huh. Oh, spiral outwards from the center. I mean, I guess that's if you played the game. That's interesting. You could do a recursive approach. Well, let's say you have a hexagon. How do you know where to draw it? Yeah, you need some kind of coordinates. So you could imagine that maybe the coordinates are part of the hexagon themselves. Maybe, as you note, there could be some kind of two-dimensional array. It's interesting to wonder how that would work, though, because it's not actually like a rectangular array. But I guess I'll just note, like, one thing you really need to do is you need the ability to, given a position, figure out where the next hexagon, say, bottom left corner should be. So I can imagine a message that, or sorry, a method that, given a hexagon, will give you like the top neighbor, the top right neighbor, the bottom right neighbor, the down left neighbor, whatever it might be. Maybe something like that. I don't know. There's a lot of approaches. Anyway, okay. So in this lab, though, you get to actually do this and explore this process and do a little bit of strategic thinking. Okay, I hope everybody enjoyed that. We're gonna wrap up here. Sorry, I went over a minute. Yeah, I had fun. I hope you had fun. I hope you're enjoying Gitlit. And if anybody is struggling, I read all the responses. I'm gonna be talking to TAs a little later. Thank you, everybody. And I will see you sometime soon. All right, I got live Q&A, remember, every Monday, Wednesday, Friday. And the next Friday, I'll be doing, instead of normal lecture, I'll do the ask me anything about my life questions. All right, that one will not be recorded though, because it's more fun. Yeah. All right. Thank you, everybody. I'm out of here.